Welcome to the solutions unit. You should have already hopefully watched the water video notes from yesterday. Those will not show up on the test. We cover water, we do a quiz over it, and we call it done. So the solutions, starting with this first part and moving forward, will be what shows up on the test. So first of all, we want to review from the beginning of the year 2 types of matter. We have pure substances, which are matter that cannot be physically separated, which includes compounds and elements. And of course, compounds can be decomposed by chemical change, elements cannot. The other type of matter were mixtures, which is where solutions come from. There are 2 types of mixtures. There's homogeneous mixtures or homogeneous, and those are what has a uniform composition, and we also call those a solution. And then heterogeneous mixture, of course, does not have a uniform composition, and that included things like suspension and colloids. And while the most of this unit is going to be over solutions, you are responsible for these review of the types of matter: pure substance, heterogeneous. Those are definitions that could show up. Okay. When we have our type of mixtures, solutions, of course, we said are homogeneous mixture, and they are evenly dispersed, and they are not the same as a chemical reaction, though, so keep that in mind. Some examples of a solution are, well, let's just go with contact solution. That would be an example. Another example would be Gatorade. It's something that looks the same throughout. And then, of course, keep in mind that there are not just solids and liquids. There's also air. It would be a solution. And even alloys. Remember, that is metals that are a homogeneous mixture. The components of a solution, this is important, is the solute and the solvent. The solute is the substance being dissolved. The solvent is the substance that is doing the dissolving. Generally, your solute will be in a smaller amount, and your solvent is going to be in a larger amount. And remember, from the water notes, we call water the universal solvent. It is really hard to keep water clean because it is such a good solvent. And then suspensions, of course, are heterogeneous, and that is the particles are so large that they settle out unless the mixture is constantly stirred. Here are you some examples that you can fill in. Italian salad dressing, muddy water, fruity pebbles, sand. Those would all be example of heterogeneous suspensions. And then colloids, if you remember, they have intermediate in size, and they're kind of between the solution and the suspension, and the particles do not settle out. We use the example of fog in last semester because it is dispersed in there. Another example would be paint, and then shaving cream is another example. So those are 3 examples of colloids. Kind of like solutions, they have a dispersed phase and a dispersing medium. So the dispersing medium is kind of like the solvent. The dispersed phase would be kind of like the solute. And then, of course, this Brownian motion is, if I were to look under it under a microscope, I could see that. And then we'll talk about the Tyndall effect. We talked about that when we talked about fog and driving on a clear night versus driving on a foggy night. Here are some other examples of some colloids. And then, of course, if you are able to see that light pass through, then that would be a colloid. And then if it passes straight through, so the difference would be, for this could be fog, and this is just air on at night. The solution process, we call that solvation, and that is the process by which a solute dissolves in a solvent. If something is miscible, that means they will actually dissolve in each other, or the solution will occur. Immiscible is when it will not occur. And a very good example of something being immiscible is oil and water. We know that those don't mix. And then, of course, aqueous solution means it is dissolved in water. So generally, I would show it like this. If I said NaCl, aqueous, that means that it has been dissolved in water. If I just had NaCl solid, that means it is not dissolved in water. So that AQ means dissolved in water. And that is going to be important in this unit, especially when we get to net ionics. Just so you're aware, it's important to realize a lot of people just think, oh, a solution is I dissolved a solid in water. There's all kinds of solutions out there. So solid in a solid, we said that would be an alloy. That's an important term to know. Liquid in liquid. If you've ever noticed, if you buy rubbing alcohol for like a cut, if you look on there, it says 70% by volume isopropyl alcohol, and that is because it is dissolved actually in water. So when we have the solution process, it depends on what we're dissolving. If I have an ionic molecule and the water is the solvent, then what happens is those ionic molecules dissociate and they become surrounded by water. So let's go back to that sodium chloride, right? If I were to add that sodium chloride and I put it into water, now this is not a chemical reaction, I just want to show you what happens, is the Na becomes aqueous and the chlorine becomes aqueous, okay? So I'm going to circle that water just so we're showing you that that's what we did, is we added it to it, but this is not a chemical reaction, so I don't want you to think that it is. I'm just kind of showing you what happens, okay? So if it is soluble in water, it dissociates and then they become surrounded, and we call that hydration, or it's become hydrated. So here is a picture of when that happens. So I have the water, and first of all, what happens is I have to break up the sodium chloride particles so they break up, but then I also have to break those intermolecular forces between the water molecules so that they can surround the ions. And then what happens, of course, since chlorine, this would be the chlorine, since chlorine is negative, the positive end of water, because remember water looks like this, and these are slightly positive, these are slightly negative because it's a polar molecule, and then the sodium right here is surrounded by the negative side of the water. Okay, so that's how it becomes hydrated. If I have a polar covalent molecule, such as, let's go with sugar, right? So sugar will dissolve in water, so let's go with C6H12O6, and I said that was aqueous. So while it does dissolve in water, it does not dissociate. So the sugar molecule would stay all as one big molecule. So you can kind of see it in this picture. And so the opposite ends of water would be attracted to the positive or the slightly positive dipoles of the molecular compound. So that's what that looks like. And then, of course, if I have a nonpolar covalent, it will not dissolve. So a solution will not occur. So that's what we would call immiscible, because it will not happen. And so you get this layer on top and then a layer on the bottom. And why is the oil layer on top and the water layer is on the bottom? And that is because oil is less dense, so it floats. If it were more dense, then water would be on top and then something else would be on the bottom. But oil is less dense, so it floats on top and you get that little layer. So that brings us to solubility. Solubility is the maximum amount of a substance that will dissolve in a solvent, and it is at a specific temperature. Generally, if we're giving you a solubility, it's at room temperature, but that solubility can change as you either increase or decrease temperature. Generally, when we're looking at it, it is usually 100 grams per 100 grams of solvent, sorry. So like if I told you that 45 grams dissolved, that would be 45 grams would dissolve in 100 grams of whatever the solvent is, generally water, okay? So we need to talk about some definitions. These are the definitions that kids tend to get messed up on the test, okay? So unsaturated means I could dissolve some more, okay? It means I don't have it all saturated. I could still get some more. Saturated means I've reached that saturation point. I can't dissolve anymore. And then supersaturated seems kind of weird, right? Because I just told you saturated was I have as much as I can. But supersaturated means that I heated it up, dissolved more at a higher temperature, and then I cooled it back down, and so now it has more than it should, and it's very unstable. That's how we make rock candy, if you've ever had that. We heat it up, we dissolve more than we should, and then we cool it back down, and then we have more than we should in there. So I want to give you an example. These are my favorite examples to use for this, for you to understand saturated, unsaturated, and supersaturated. And that is going to a restaurant, we're in Texas, and going to the restaurant and ordering sweet tea. And they say, I'm sorry, hon, we don't have any sweet tea. We only have unsweet. And so they bring you some unsweet tea. Well, obviously it's unsaturated. It doesn't have anything in there, right? And so I pour some sugar in there, and I stir, and of course it's iced tea, and I stir it, and all of a sudden I let it settle, and I see this layer of sugar down the bottom, and I taste my tea, and it doesn't taste very sweet. It's a little bit sweeter, but it doesn't taste very sweet because I have reached that saturation point for that temperature. But then if I go home and I decide I'm going to make my own sweet tea, how do I do that? I boil my water, I make my tea, and while my water is hot, I dissolve my sugar, and then I ice it down, and then it's nice and sweet. Well, what I'm actually drinking when I drink sweet tea is a supersaturated solution. And if you've ever left a pitcher of iced tea in the refrigerator for a really long time and forgotten about it, sometimes you'll come back and there'll be like a big giant layer of hard sugar down at the bottom because it is unstable, and eventually it will dissolve. It will settle back out and recrystallize because it is supersaturated and unstable. Okay, so now I want to look at a solubility curve. Okay, and that's what your notes. That's pretty much. We're going to go a little bit further than that. I got to see where we're going to end today. But I need you to know how to read this, and this is what your worksheet is on that is due tomorrow. Okay, so when I'm looking at this solubility curve, notice this is grams per 100 grams of water, okay? So if I am on the line, so on the line means that is the maximum amount. So on the line would be saturated, okay? That means I'm at the maximum amount that I should have for that temperature. So on the line is saturated. If I'm below the line, so we're gonna use our examples for NO3. So let's say I had told you that and we're gonna do 40 degrees. Okay, so if I said, hey, at 40 degrees, I dissolved 70 grams of sodium nitrate, and that would be right here, okay? So this right here is under the line, so under the line would be unsaturated. So that would be under the line because I have not reached the point where I need to yet, okay? Now let's say that I told you, hey, I heated the water up and I dissolved 130 grams, okay? So I heated the water up to 60 degrees. Okay, no, let's go with 70 degrees. So I heated it up to 70 degrees, dissolved 130, and then I cooled it back down to 40 degrees, okay? So I'd be right here. So now I would be supersaturated because I'm above the line. Okay, so if it ends up being above the line, it's supersaturated. Okay, so what I could do from that is I could literally calculate how much would precipitate out when I cooled it back down. Okay, and so what I would do is I would take that 130 that I heated it up to, right? And I dissolved 130, but then at 40, my saturation point is, it looks like about 105. So then that means I could get 25 grams to precipitate out because I'm over the line at that point. Okay, so that's how that works. Okay, the other way this works is, let's say, okay, I'm going to tell you, hey, I want to know how many grams. We'll still stick with the sodium nitrate. How many grams of sodium nitrate could I dissolve in 200 grams of water? Okay, so if I have at 100 grams, I said of water, I could dissolve 105 grams. At 200 grams, it's twice as much, right? So it could be 210 grams. So that's how that works, okay? So moving on, we are going to talk about the factors that affect our rate of solubility, okay? So we're not necessarily talking about how much it will affect here. We're talking about how fast it will dissolve, okay? So not necessarily how much, but how fast. And the fastest way to do this is heat it, crush it, stir it. Those will affect how quickly something will dissolve. Again, not necessarily how much, but how quickly, okay? And it talks about all that, but it's all about introducing fresh solute and solvent, okay? So I'm going to go back to our iced tea example, right? So most of you have probably at least seen iced tea made in your life. So what do you think is going to dissolve the fastest? If I have the crushed granulated sugar or sugar cubes, okay? So, like the little sugar cubes that, they feed horses and things like that. If I have a teaspoon of crushed sugar and a teaspoon, which is what a sugar cube is, the teaspoon that's been crushed is going to dissolve faster because now I have them all crushed up, whereas on the sugar cube, I've got layer by layer by layer, okay? So crushing it, you want to increase the surface area, okay? So this is where the crushing goes in right here, is increased surface area. Okay, and it seems counterintuitive. You think, oh, well, a sugar cube is bigger, but we're talking about the surface area of all the particles. So by crushing it, I can spread that out, and I actually have a larger surface area. Okay, stirring or agitation. Let's say I'm making a big pitcher of iced tea, and I just put my hot water in there, and I just dump my sugar in there, and then I just leave it be. Okay, it does not dissolve as quickly because what happens is the layer of water right above all that sugar you dumped in there gets saturated, and so it's not going to take any more sugar into that layer, and so you have to stir it so that you can constantly be introducing fresh solute water to the sugar. And then of course temperature, what happens to the particles as I increase the temperature is the particles are moving faster and faster and faster, and so they're colliding more with the sugar. Okay, so heat it, crush it, stir it. That's what you want to do to get this to dissolve quicker. Again, I'm going to say it a third time. This is affecting the rate, not necessarily how much. Okay, so heat it, crush it, stir it. Now, factors that are affecting the solubility, so this would be how much. Okay, this would be how much, not necessarily how fast. And again, temperature comes into play here, but you have to be careful because it generally, notice I said generally, if I'm trying to get a solid to dissolve in a liquid, generally if I increase the temperature, I will increase how much it goes up. Okay, generally, not always. So that's when you would look at the solubility curve, okay? So most of those things are going up. Interestingly enough, if you notice sodium chloride right here, it actually does not change that much with temperature. Very little, very, very little. And some things actually even go down with their solubility. Here's an example right here. The cerium sulfate, it actually decreases with temperature. So that's why we say generally. Most things do go up, but sometimes you without knowing, you would need to look at a solubility curve, okay? However, on gases, the temperature has the opposite effect. Decreasing the temperature increases solubility of gases, okay? And if you notice all these gases, they actually go down, okay? And that's always what I like to ask you here. Would you rather drink a hot Coke or a cold Coke? A hot Coke goes flat way faster than a cold Coke. That's why it's better to drink it cold. But if you have a warm temperature or room temperature Coke, it goes flat a lot faster because as soon as you open that up, the gas starts escaping faster. So cold Cokes actually hold their fizz longer. And then pressure is only affecting gases. So this is for gas in a liquid, okay? Gas in a liquid. And here is a formula. You do not have to do any calculations with it. Henry's law says that at a given temperature, the solubility of a gas is proportional to the pressure above the liquid. So I want to ask you, we just talked about Cokes a while ago, what happens when you open that Coke? What sound do you hear? And all in your head, you're going, psht, you hear that little psht. And that is because in order to get the CO2 to go into your Coke, there is a layer of pressure on top. That's why it doesn't go all the way to the top. There's always a little air pocket in there, and that's because they have to put pressure on top of that Coke or Dr. Pepper or whatever you like to drink to keep its fizz. And that's why as soon as you open it, even if you close it back, eventually it goes flat because that pressure has been released. Okay, and it is directly proportional. The more pressure on top, the more gas you can get to dissolve in the liquid. Okay. And then when we talk about solution proportions, you may have heard me say this in the lab when we're talking about acids or bases, and I say concentrated solution versus a dilute solution. Concentrated is a relatively large amount of solute, and diluted is a relatively small amount. An example of a concentrated solution, think Tide Pods, right? Tide Pods are very concentrated, or if you have more diluted, you get the big jug of laundry detergent, and you have to use more of it than you would in a Tide Pods. So that would be an example of concentrated versus dilute. And then lastly, we're going to talk about electrolytes versus non-electrolytes, and it will depend on whether the particles can move around. So electrolytes are compounds that conduct an electric current in aqueous solution. Okay, some example of some electrolytes would be like aqueous sodium chloride, or strong acids like HCl is a strong acid. Okay, those things would conduct electric current. So strong electrolytes are aqueous solutions of, it says of all ionic compounds, I want you to add that are soluble. Because if they're not soluble, then they're not going to be, that are soluble. Okay. Also, our strong acids, 1, 2, 3, 4, 5, 6. We've left some out. 8. So I brought no clean clothes. Nope, that's it. So yeah. So this is a way to remember that. So I brought no clean clothes. That's a way to help you remember what those strong acids are. And of course, here they start with those things like that. We have nitric acid, so sulfuric acid, hydroiodic acid. Those are ways to remember that. Strong bases, that's going to be group 1 and group 2 hydroxide from calcium down. You're going to get this when we do net ionics in a day or two. Weak electrolytes are things that only a small portion will dissolve, and so it's a weak weakly conduct electric currents, and so that's going to be your weak acids and your weak bases. And then a non-electrolyte is something that does not, it's aqueous, okay, but it doesn't conduct electric current, so that would be example of like sugar water, what we talked about earlier. While it will dissolve, it doesn't dissociate, okay. And of course, we left out this molten state, so if I had solid sodium chloride and I melted it and it became molten, then it actually would be an electrolyte. Okay. And that is just a little picture to kind of show you what that looks like. And I think that's where we're ending. Yeah, we'll pick up with concentration of solutions on our next lesson.